Okay, so there's two kinds of fly scans, the kind that nobody ever does and the kind that everybody thinks is the only kind of fly scan that there is. That's basically the situation at APS now. The software fly scan is what I described in the last talk, the scan record just doing the motions of a software fly scan by launching a positioner to the end, and then trigger, and all reads. And nobody ever does that, and people really should, because for alignment, it's so easy. You don't need any cabling. You don't need anything except a positioner whose speed you can set and a detector whose dwell time you can set. And that's what we have. That's what motors are, and that's what scalars are. So I kind of think that should be more widely used, but whatever. People do what they do. The hardware fly scan is what people almost always mean, and this requires a cable. This requires a hardware trigger from the motor to the detector. And the scan record is really not doing very much in a hardware fly scan. Most of the stuff is actually, it launches things, but most of the stuff is actually happening in the hardware. So for a hardware fly scan, in both cases, the data are acquired while the positioners move. That's what makes it a fly scan. Detectors are triggered by pulses from a positioner, and that can either be periodically or at user-specified points. There are lots of variations on fly scans, as I'll show you. And you can acquire the positions yourself, or they can simply be implied by the fact that a trigger came and you told it where to send the triggers. And that's normally what happens. There isn't any dead time, well, there's nanoseconds of dead time between the points. And you do need a cable from the selected motor to the selected detectors. So it's a lot more setup, but so then there are two kinds of hardware flies. There's constant speed, which you could do with a motor, because the motor is only going to move at constant speed. And then there is a trajectory scan, which is just like, it's the same as a normal hardware fly scan, except that the motor can slow down and speed up, and you have to tell it what trajectory to follow. But other than that, it's just a fly scan. So in this case, the positioner moves in the constant speed. Obviously, the positioner moves at constant speed, and it can be moved by a motor record, and all you have to do is specify the start and the end position and the number of points and the motor speed. And in some cases, with some motor types, you might be able to specify the positions at which data are acquired. You might be able to say every 1/10 of a degree, or you might be able to actually specify 0.1 and then 0.32 and then 0.78, whatever. For a trajectory scan, the motor moves along a trajectory that's specified by positions and times, typically. There are other ways to specify it. And you use the trajectory controls and not the motor record. And you normally specify data acquisition positions, although there are some constraints. The motors are all different as far as this goes. And it requires a motor that is explicitly supported to do trajectories. So here's what a software fly scan looks like. Here's the difference between a step scan and a software fly scan. It's just two things. One, you just tell it that it's a fly scan, and the other one is you have to set the motor speed. Well, you also have to set the detector dwell time. I didn't include that. The synchronization, as I said, is imprecise, and you can't go that fast. 10 hertz, maybe 20 hertz, something like that. It's probably as far as fast you can probably go. It all depends on how fast the motor updates its position, right? So for a hardware fly scan, you need the positioner to be able to output pulses during some kind of a move. All stepper motors can do this because that's how they talk to their driver. They send out a series of step pulses. The Aerotech Ensemble can do this with the Ensemble PSO Fly database, and probably other servo motors can do this, but I don't think software has been written for any of those guys to do it that isn't also trajectory software. You need a hardware trigger detector, and it needs to know what to do with it. It needs to be capable of either one, storing or streaming or whatever, doing something with the data so that it won't just spill on the floor when the next detector trigger comes in. So the multi-channel scaler is one example, a DXP, and there's now a lot of cameras. And then you need a data storage client. The scan record can store some kinds of data, as I said, any array data. Some people use spec to directly grab those arrays out of the IOC, and more commonly these days we use an area detector plugin to write a completely different data stream. So hardware fly scan, there's actually quite a few changes. This is the way hardware fly scans are normally done with the scan record. There's lots of different ways to do this, but normally there's a before scan length that starts the detector, because the detector has to be ready for trigger pulses, right, before you start the motor. And you don't wait for that guy, because it's going to be acquiring throughout the scan as long as the motor's moving. And you don't read back any positions. Those are going to be implied by the locations at which detector triggers were sent. You don't trigger any detectors, but you do want to read the arrays, if this is a multi-channel scaler, for example. And then after the arrays after the scan is finished, you probably want to trigger the multi-channel scaler to tell it to read all of its data, or in this case, stop. And then you have to set up the multi-channel scaler with a reset, with a dwell time and prescale, stuff like that. The prescale, if this is a motor, or a stepper motor, then you're probably going to be connecting step pulses to the multi-channel scaler, and you probably don't want to acquire data at every motor step. That would be ridiculous in most cases. And so what you do is you tell the multi-channel scaler, every 730 motor pulses, I want a data acquisition trigger. And so the multi-channel scaler has that preset, has a prescale counter inside of it. You want external channel advance, and normally you want a clock as the first channel, just for diagnostics afterwards. So the positioner speed has to be set, and the detector has to be prepared and has to be started before the motor starts moving. So a trajectory scan has the most requirements of all. The controller has to be able to do it, and normally that's a servo motor. Well, that's not anymore. It used to be just servo motors could do this, but now the OMS can do not a really perfect job, but a pretty good job. As long as you don't have to move really slow, the OMS controller can make stepper motors do a trajectory as well. So the controller has to be able to generate position-synchronized pulses of some kind. And you're going to need somebody to generate an array of positions and times that makes a trajectory. So it could be SPAC or an array calc or Python or somebody. And you need a hardware trigger detector just like before, and you need a data storage client just like before. So in the bottom 2 points, this is just the same as a constant speed fly scan. So these are the user interface changes, assuming that you're going to do this with a scan record. And the first thing is, if you're going to do this with the scan record, why? Because the scan record doesn't really help very much, right? All you're really doing is executing and then reading the data. So a lot of times people will do this directly with a client, with spec, for example. That's what's happening in most of the cases that I've been involved with. Oh, and there is the trajectory support, which I'm not going to talk about in great detail, because that's really another talk, I think. Because this is mostly about the scanning implications of this. But so, the requirements, a trajectory has to be loaded in advance, and you have to prepare the detector. So to define a trajectory, you have to define the number of elements, an array of positions, an array of times for each motor, an array of positions for each motor in the case of the MM4000 or the XPS, because those guys can do multiple motors. So far the Ensemble can't do that, or it can, but I can't tell it to do that. And then you have to describe the pulses that you want. And that's where the motors are most different. The MM4000 can do pulses evenly spaced in distance along the trajectory. It's not along any one motor, it's along the actual curve. The XPS can only do pulses evenly spaced in time. So it will do the number of, it knows how long the trajectory is going to take to execute, and you tell it how many pulses. For the Ensemble, you can either have the pulses evenly spaced in distance, and there's only one motor, so the distance is not ambiguous here. Or you can have it send out at trajectory points. And this is no longer under development. You can also tell it to send out pulses at user-specified points. You can tell it how many pulses to send, which positions to send them out. For the Max-V, the only option is pulses at trajectory points. The MM4000 and the XPS have absolute, relative, and hybrid position mode. And basically, this is pretty much absolute and relative. And the nice thing about it is that you can download a sort of a master template trajectory and then change the start point and execute that trajectory relative to that start point. You can do this with the MM4000 and the XPS, but I haven't written that support for the Ensemble or the MM4 or the Max-V yet. And the Max-V has timing problems in very slow motion because its time is basically the counter that is going to deliver step pulses. So if you get step pulses coming very, very slow, then your timing is going to be commensurate with the 1 over the frequency of those pulses. That's going to be the timing and precision. So here's another way to look at fly scans. The basic thing you have to have in all fly scans is a divide by n. And that's either going to be dividing the motor pulses by n, where you don't want to take data at every motor pulse. Or you can also, as Kurt demonstrated, you can also take an encoder value and generate quadrature signals from that and have a divide by, and drive a fly scan with the encoder pulses. And in that case, you still need to divide by n. The multi-channel scaler has a fixed divide by n. So all you really need is a motor or an encoder and a multi-channel scaler, and you could do a fly scan. But the other possibility is to have, if you want to be able to tell the motor controller at which specific positions do you want detector triggers, then you need a variable divide by, you need a programmable divide by n. And the Ensemble has one of these inside of it, in the controller, and there are commands that allow you to tell it which positions. If you're using a stepper motor or a motor that doesn't have this capability, a servo that can do a trajectory but doesn't have the ability to send out pulses at user-specified places, you can do this with softglue. Softglue can implement a divide by n that's programmable, and each time a pulse comes out, it will write the next value out of the array into the divide by n. So I think for almost any motor at APS, you can do some kind of a trajectory scan, certainly some kind of a fly scan, a hardware fly scan, and for many of them you can do fly scans in which the data acquisition locations are specified in an array. So here are some examples. I don't know if these are really all that interesting. Well, I guess it shows a variety. At one IDE, they're using an Ensemble PSO fly with evenly spaced, not trigger signals, but gate signals that tell the detector for how long to acquire. And the problem there is that the detector needs some finite time to recycle. So the gate goes up until the next trigger is due, minus the recycle time. At 2BMB tomography, they're doing, and also 32 IDC, you're using Ensemble PSO fly, and they have evenly spaced data trigger signals. 2BMB also has an interlaced fly that uses the soft glue technique that I was telling you about that allows you to specify the positions at which the data acquisition triggers are generated. It used to be 15 IDD, now it's 9 IDC, this is sector 9. Does a multi-motor trajectory scan where the rotation stage is driven by a servo motor and it executes an exponential trajectory, and then there are translation stages that just keep up with that. Just execute commensurate trajectories. And the last thing is, it's not really a trajectory scan, it's just a trajectory, because for gradient mirror deposition you want to be able to vary the speed at which the depositor, or at which the mirror moves, and basically what you're doing is varying the thickness of the deposited coating. That's been installed, but it's not connected to higher level software, so it's not really active yet. So, plans and possibilities. We could do a better job of supporting fly scans, making it easier to start a fly scan. I haven't really looked at that yet, but probably should. We will probably soon have Ensemble multiple motor trajectory support. I've been for years wanting to do an insertion device and monochromator fly scan, and we came pretty close to doing one, but the beamline evaporated before we got a chance to run on it. And then other sort of miscellaneous technical improvements I like to do. So that's all I got to say about scans today.